So, looking at base strength of amines today, just someone explains to me why is ammonia a base? Go for it. Yeah. Can it accept a proton? So in doing that, and it's reversible, of course, because it's a weak base. In doing that, it has to use. How does it get that proton on board? Has a lone pair of electrons. So when we think about the bond between the NH3 or the nitrogen and the H plus, we know it's what kind of a bond? Dative covalent bond. So that lone pair has to be available to be given away to the H plus. Okay. We can measure pKa. We have come across pKa before. It's kind of measure of acidity, but you can have a pKa value for a base as well, for reasons that I'm not going to go into now. And pKa for ammonia is 9.25. Okay. So the higher the value, the stronger the base. The lower the value, the stronger the base. Okay. So we're talking about amines. What effect does it have if I put an ethyl group on that nitrogen? What effect does it have on the lone pair of electrons if I put an ethyl group on there? A little bit of this would depend on whether you've read ahead or not, or what you might remember about ethyl groups. Just while you're pondering that question, I'll just write some stuff down over here. Okay. So it's a bit of mechanism. You might remember the electrophilic addition mechanism with alkenes. Why is that related to our discussion about the base strength of amines? What's the link here? Go on. The positive inductive effect. Could you explain to us what the positive inductive effect is? Okay. Which of these two structures is making better use, if you like, of the positive inductive effect? The bottom one. So what is it that's going on that makes this preferable? No?
To do with the electrons and the two bonds next to it, and they like move towards it, don't they?
Okay, that's exactly right. That's what the positive inductive effect is. It's the movement of electrons down an alkyl chain. So there would still be positive inductive effect there as well. Ethyl group isn't quite as strong as two methyl groups, so the positive inductive effect is strongest for that carbon there. What's the effect of that? Let's just complete this bit of reasoning before we go on. Go on, Boris. Okay. Stabilizes the. What would be a description of those two? To this one rather than that one. What? Secondary carbocation intermediate. Yeah. Positive inductive effect stabilizes the secondary carbocation intermediate more than the primary, so that's going to hang around for longer, so that's more likely to produce the 2 bromo propane rather than 1 bromo propane. So 2 bromo would be the major product. Okay. How does that relate to this? So we're not comparing secondary with primary carbocations here. We're comparing ethylamine with ammonia and its pKa value. We'll come to the pKa value, but what's going to happen with our ethyl group here? Yes, Chris, go on. It's going to push electrons towards the nitrogen, exactly the same way as we had over here. It's going to push electrons down. So, remembering that the lone pair has to leave, has to be donated, or has to be available to be donated, is that going to make it more available or less available if we're shoving extra electron density down the chain? More. Okay. So the lone pair on the nitrogen is more available, and I'm writing this down because it's the kind of thing you're going to have to write in your exam answers. Yeah, more available to be donated. If it's more available, if it can give away those lone pair of electrons more easily, it can attract the H plus more readily, which means it's more likely to form the ammonium salt, which means it is a stronger base. pKa, let's put it over here, pKa equals something bigger. I forget what it is. Ethylamine 10.73. So again, a larger pKa, just like the pH scale, right? A larger number is a stronger base. A larger pKa is a stronger base for ethylamine.
So it's 10.64.
What? What, sorry?
It's 10.64, not 10.73.
That's methylamine. Is 10.64. Oh, okay. Yeah, and it says pKb in the table as well, so I don't know where I've got that from. I've just copied the wrong numbers in, I think. I'm looking at this very worthy chemistry data book from Andrew Prescott 5C. So that dates it to when we used to say year 11 was the 5th form. First published in 1969, reprinted in 88. Yeah, 88. Okay. So, yeah, hasn't changed since 1988. Definitely 10.73. All right. What would happen if I put 2 ethyl groups on my nitrogen? So what an H? Higher, lower? Higher, yeah. Not much, actually. What have I got? Diethylamine 10.93. Okay. What if I put 3 on? Oh, goes down. Does anyone know why? What has that got that hasn't? Or what can that do that can't? Go on, follow that. Something to do with the hydrogen, yes. Which enables it to do what? What do you need an NH bond for? Someone's got this. Go back to your properties of amines. It is very good. Hydrogen bonding. Well done. Right, so that can hydrogen bond, that can't. Why might that make a difference? This is hard, but this is kind of, random stuff they throw at you in the exam. Why might that make a difference? Very good. You're on fire today, aren't you? Yeah. It's not water soluble, or it's almost insoluble. If you can't dissolve, it's quite hard to, do the aqueous ion thing. So, yeah, because the triethylamine is less soluble because it can't hydrogen bond in the same way that can. It would still mix with the water, but not nearly as soluble, so it can't have as higher pKa. Anyway, that's not really relevant. It's just interesting. Let's move on. What happens? Let's get rid of my positive inductive effect. What happens if the amine is sitting on a benzene ring? Aha.
Oh, it's going to be so low. What a guess.
What do we know about the benzene ring? Tell us about the benzene ring and why we draw a circle. Sam, tell us all about that.
There's a ring of delocalized electrons.
Okay, ring of delocalized electrons. A pi cloud, you might call it. Yes. Okay, ring of delocalized electrons. And here we've got some other electrons not doing anything in particular. What happens next? What might happen to those lonely, bored electrons? There's a big pi cloud party going on next door. Well, you'll always get hydrogen bonding wherever you've got NH bonds, yes. But I'm just talking about those electrons there in particular. There's a big, washing machine of a party going on here, swirling around. They go and join the parties, exactly right. The electrons on the ring there. Yeah, that's fine. They kind of get pulled into the ring. Okay. Does that make them more available or less available if they've been pulled into the ring? Less available. So it's the exact opposite effect here. So now we've got the lone pair on the nitrogen is delocalized in the ring. And less available to H plus or to be donated. So it's a weaker base. I had some data somewhere. Oh, here we are. 4.62, is that what it says there? Is that different again? No. So pKa 4.62, so very weak base compared with ammonia 9.25. So in terms of overall base strength, then we've got kind of ammonia in the middle here, and then ammonia is a weaker base than any alkyl amines, but it's a stronger base than any phenyl amines. That coming up? No? Yes? No? Press the button, did I? Yeah. Okay. Let's just have a quick look at a question, if you can read it. I dug out this chappie here as well. What would we call this? Diphenylamine. Has a pKa of 0.8. It's practically an acid. So yeah. Right. So here's a fairly standard question on base strength. Don't know whether you can read that, but we've got three bases. Just the phenylamine. We've got that's, what is that? Phenyl aminoethane. Yeah. And phenyl ethyl amine. And you have to put them in order of increasing base strength and explain the difference in base strength of those three amines. Could you do that for me now, please? It's worth some marks. 6 marks. That is worth.
That's a good question.
Okay, let's see if we can get all 6 marks for this. Somebody want to start us off? You only get 1 mark, Sam. I might come back to you in a minute. Let's get one comment from one person. Philin, let's start with you, please.
I think Amine E is the weakest base.
Amine.
E.
Because
The lone pair of electrons which are unbroken is in the localized ring, so on
what was the second part of that statement?
Is into the ring and less available to treat their neutrals.
Thank you. Jake, could you give us another? What was that? I didn't really get any of that. G would be next. Okay. So F is the strongest then. So let's just start with that. Because is positive inductive effect. Yes.
Isn't G the strongest? I mean the weakest, sorry. Because the positive inductive effect pushes the electrons closer to the benzene ring.
No.
So they're further away. And
No.
they're closer to it.
No. G is has a combination of E and F. The G's in the middle. E, you've only got the electrons being delocalized into the ring, and in F, you've only got the positive inductive effect going down the alkyl chain. In G, you've got a combination of the two, so to some extent they'll cancel each other out. Okay? Okay. All right, we're mostly there. This is the mark scheme. So there's a mark for saying the base strength depends upon the availability of the nitrogen's lone pair. which perhaps because we've just done it in class, you've kind of taken as read, but of course in the exam you do have to state the obvious. So we've got E, the lone pair next to the ring is delocalized, so it's less available. Tick tick. For G, the positive inductive effect pushes the electrons along to make the lone pair more available. Tick tick. And then the last one is just for saying the order of increasing base strength is E, then G, then F. Okay. Okay. We could just take your minds back to what we did last time, which was nucleophilic substitution of haloalkanes using amines, using ammonia to make amines. Base strength is all about the availability of the lone pair to be donated. Isn't that very like nucleophilic strength then as well, because nucleophiles are electron pair donors, and this mechanism happens because the lone pair on the nitrogen can attack the carbon, and we know that pKa for ethylamine is higher than pKa for ammonia, so it's a stronger base, so it's likely to be a stronger nucleophile. And if it's a stronger nucleophile, then surely our ethylamine would be more reactive than bromoethane than ammonia would. This is all true. This is... Did you say a plot twist? Ethylamine is a stronger base and a stronger nucleophile than ammonia. So, what's going to happen if ethylamine and bromoethane meet up? They're going to react. What will that mean? Just think it through mechanistically. You've got your bromoethane, and you've got the nitrogen on the end of the thing, and we've got a lone pair there, and we've got an attack that's going to happen there, and we're going to lose one of them. What's that going to make? Yeah, we've got an N. We'd have to lose an H plus, but once that's happened, we're going to have diethylamine and some other stuff. But diethylamine is a stronger base than ethylamine, isn't it? So it's going to be a stronger nucleophile as well. So there's going to be some other stuff there, but it's all going to happen again. Plus some other stuff. Now we know that triethylamine is actually a weaker base, but That's just because of its solubility, right? The lone pair of electrons is going to be more available than for diethylamine. So actually, even though it's a weaker base, it would still be a stronger nucleophile. So we can keep going. 3. And what's that going to make? Yeah, we have to, if it's ammonium, we have to have the bromide as well. Yeah. So tetraethyl ammonium bromide. Yeah. Yes. So that's going to be a big mess. Well, when you're doing any kind of organic synthetic reaction, what you want is to have one product, please, or one product and something that you could easily remove, dissolve ammonium bromide in water. So that's fine. What you don't want is like 5 different products and 8 different byproducts. That's about as messy as you can get. So we'll come back to the tetraethyl ammonium bromide in a moment. How do we stop that all from happening? If I'm doing a synthetic reaction and I just want to make ethylamine, how do I make that happen? How do I tip the odds in my favour? Think about it from the bromoethane's point of view. You're bobbing around in a round bottom flask somewhere, and you could bump into ammonia or a more reactive amine, diamine.
There's a high concentration of ammonia.
Massive concentration of ammonia. So generally you use like 100-fold excess. If you have 100-fold excess of ammonia, then even after lots of the bromoethane has reacted, you're still 100 times more likely to bump into another ammonia than you are to bump into the ethylamine. Unfortunately, because ammonia is so soluble in water, you can have really, really concentrated ammonia. The conch stuff that we always put out in the fume cupboard is called 880 because that's actually its density. It's got so much ammonia in it. Its density is 0.88 grams per cm cubed. So we can have a massive excess of ammonia, and that stops the bromoethane from being likely to bump into any amine products. Okay. There was one more thing I was going to say. Yes, there was. There is an advantage in making tetraethyl ammonium bromide. The quaternary ammonium salts. Try saying that when you've got a mouthful of marshmallows. Quaternary ammonium salts are useful. What are we looking at around the room here? Okay. It's a particular product I was looking for, but I don't think anybody needs it. Fabric or hair conditioner. But nobody's got long hair in here. You're all quite, shorn. Do you understand the concept of fabric or hair conditioner? If you don't use it, you might not. Hey? Does not trap moisture? No. Does anybody use hair conditioner? Richard does. What? Why do people use hair conditioner or fabric conditioner for that matter?
So it's like softer.
Right, makes your fabric or your hair softer. Okay, so have you ever had? This is going to involve some fairly detailed laundry details here. But have you ever had a towel that's been in your house a long time? Dog towels are good examples because they go through the wash a lot, and they get hard. Anyone got a hard towel?
Great.
Yeah. Has anyone bought a brand new towel and tried to dry yourself with it? You know, when they're really, really super fluffy, you buy them from the shops. They always make them as fluffy as possible. They don't dry you. They just sort of wipe the water across your skin. It's very weird. So, what's going on there? Right. Well, either the hairs or the fabric consist of these long molecules or long collections of molecules, and they get charged, and the charges mean that they will. Sorry, we need some minuses in there. The charges mean that they will tend to stick together and tangle. So if you have long hair, then your hair will get tangled. So you use lots of hair conditioner, and then your hair stops getting tangled because literally the hairs are not attracting each other. It's it's an ionic attraction, and it's the same with the fabric in the towel. The little hairs in the toweling will get attracted to each other and mat together, and that's when your towel gets hard. So the fabric conditioner is your quaternary ammonium salts. So the positively charged quaternary ammonium salts sort of stick to the sides of the strands of hair or whatever it is, and then all of those long alkyl chains all kind of hang down. This is a terrible diagram. Okay, so the nitrogen stick to the hairs or the fluff on your towel, and the alkyl chains, they often use quite long alkyl chains, kind of hang down. So all we've got between the hairs now is the very weak van der Waals intermolecular forces between the chains, which means that they tend to separate, and which means that they tend to not stick together. Trouble is, long carbon chains do not dissolve water. They're non-polar, so they don't pick up polar molecules like water. So if you have a fabric conditioner towel, it won't dry you. It'll be lovely and fluffy, but it won't get you dry, which is how they come from the shops. And when you get your towel, when you buy your new towel set from Dunelm or wherever it is, the first thing you have to do is soak it in cold water and then wash it without using any fabric conditioner. And then that'll get rid of the fabric conditioner that they put on in the factory to make them nice and fluffy, and then it'll start drying you when you step out of your shower. All right, you now know more about towels than you ever thought you needed to know. That's a life lesson. There we go.